At this point, I think we have one piece of the puzzle that's left. We've established the relationship between a definite integral and an area under a curve, but we have yet to come up with an algebraic way of figuring that out beyond using area formulas for triangles and rectangles and so on. So I'm going to switch gears here a little bit and ask a slightly different question, and that is, given a function f at x equals 3x squared, can you tell me a function whose derivative is going to be that? So give me an original function, we'll call it for now, so that the derivative is 3x squared. And I think if you are comfortable enough with derivatives, this is just sort of a matter of fiddling around and thinking backwards for a moment. We can fairly quickly establish that, in fact, we could use the function f at x equal to x cubed. And just checking that with satisfied the request there. And my next question for you is whether or not that's the only option. And I think we can pretty quickly say no, because we know that the derivative of a constant is 0. So for example, if we looked at f at x equal to x cubed plus 1, we've got exactly the same derivative, because the derivative of x cubed is 3x squared, and the derivative of plus 1 is 0. And same thing if we add any constant that you could think of there, add or subtract. So we could take f at x equal to x cubed minus 700, and that function has exactly the same derivative. Any constant you can think of isn't going to change the derivative. So we're going to get a little bit more into the notation here. We say that f is an antiderivative of little f if we're in a situation where the derivative of big F gives us little f back. So we're working backwards from a derivative. If we know one antiderivative, then we can talk about the family of antiderivatives just by adding a constant c. And I think it's also worth noting there before we move on that there's not a special reason that I'm using big F and little f, that we use little f to talk about the derivative and big F to talk about the antiderivative, or what we might call the original function. We can also call an antiderivative an indefinite integral. So that process of antidifferentiation is the same as integration. And indefinite is the word we use when we don't have any bounds. So attached to that integration sign, we don't see any numbers telling us the bounds of integration. That's what we mean by indefinite. If we're looking at the notation there, we say, if we're reading the whole thing from left to right, we would say that the integral of 3x squared with respect to x is x cubed plus c, and c is our constant of integration. And the function that we're integrating, the 3x cubed, is called the integrand. Those are terms that you might hear as we move forward. Before we establish some basic rules, I think let's try using what we already know about differentiation to work backwards for some of these. In part A, you're asked to find the integral of x squared. And we know that taking a derivative knocks that power down by 1. So I think we expect to see something cubic. But let's stop for a moment there. If we take the derivative now, we would get a 3 in front. And we don't have a 3 in front in that integrand. So I think the way to fix that is to multiply by 1/3. And don't forget your constant. That's something that you'll have to remember as we move forward with indefinite integration. So let's check it quickly by taking the derivative. If you bring that 3 in front, it cancels out with the 1/3. The power after we take a derivative is x squared, and it does in fact work for us. Let's try another one. Because it's cubic, we are expecting something to the power of 4. But we know that when we differentiate and bring that 4 in front, we are going to need a 1/4 there to cancel out. Check it by differentiating. Bring the 4 in front, the 4 cancels with the 1/4. we knock that power down by 1, and we get our x cubed back. The last one is slightly different because there isn't a variable. We're asked to find the integral of 7 with respect to x. So think about when you would differentiate and get a result of 7. And of course, that's when you start with 7x. We know that the derivative of 7x is 7. And again, we do need that plus c because we could add any constant to that and it wouldn't change the result. We do know enough now to come up with some basic rules of integration. And as we work through the list, I want you to always be thinking about working backwards from a derivative. So in the first one, the integral of 0 with respect to x, think about when we would get an answer of 0 for a derivative. And that's when we take the derivative of a constant. Say 4. The derivative of 4 is 0. Any constant, that's true for. The next rule there is something that we saw in the previous example in part C. It's the integral of a constant, and that comes from differentiating kx plus c. Again, think of something with numbers if it helps you. If we took the derivative of 4x plus 7, we'd simply have 4 left. The next one there is similar to what we saw with definite integrals when we had the bounds. We can just pull out that k. And that rule is more about telling us how integrals behave than finding an actual integral. And again, it is okay to split up two integrals when we want to find the sum or the difference. So the next rule tells us that we can take the integral of f at x with respect to x and add or subtract that to the integral of g at x with respect to x. The next one is probably the most interesting one we've seen so far, and it's a generalization of what we saw in part A and B from the previous example. If you have x to some power, we know that we are going to increase that power by 1. So we'll see x to the n plus 1. But to cancel out that n plus 1, when we bring it back in front, we do need to multiply that by 1 over n plus 1. Again, numbers might help. If you think of n as 4, if we want the integral of x to the 4, we're going to get 1 over 5 times x to the 5. And there is a note there that n can't be equal to negative 1. We'll deal with that a little bit later. The last 6 come from reversing our trig rules. The integral of cos x with respect to x is sine x plus c, and I've missed the plus c above as well. And we know that because when we take the derivative of sine, we get cos. So I'm just going to fill in the rest fairly quickly here. The integral of sine is negative cos x plus c. And again, think about working backwards. If we wanted to take the derivative of cos x, we would get negative sine. The two negatives cancel out, and we have our sine x as we desired. And let's flip around the last 4. We get tan x plus c here because we know the derivative of tan x is secant squared x. Similarly, we get secant x plus c here, negative cotan x plus c here, and for the last one, negative cosecant x plus c. And let's try a little bit of practice before we move on here. In part A, we can use the constant rule to bring that 4 in front. And really what we have to worry about there then is the integral of x to the 7 with respect to x. So using the 5th rule on the page there, we know that that's going to be 1 over 8 simplify that a little bit, and we'll get 1 half x to the 8 plus c. And at that point, it's always a good idea to check by taking a derivative. If you bring that 8 in front, we have 8 times 1 half is 4x to the 7. And 4x to the 7 is what we started with, so it appears that everything's okay there. Before we try b, it's probably helpful to rewrite that as x to the power of 1 half. And then we can apply the same rule. We can increase the power by 1 and divide by that same number. So if we take 1 half plus 1, we get 3 halves. And we have 1 over 3 halves. Just make that look a little bit more like a 2 times x to the 3 halves plus c. And of course, when we divide by a fraction, we flip and multiply, so we get 2/3. Let's check it. When you bring that 3 halves in front, the 3 halves and the 2/3 actually cancel out completely. We reduce the power by 1, and we're left with x to the 1 half, which is exactly what we want. The last thing I want to expose you to is the fundamental theorem of calculus. We're not going to go into a great amount of detail here, but it's the formal statement that actually says that differentiation and integration are opposites. So if you take the derivative and then undo your work, what you're actually doing is integration, and that does tie back to the area under the curve. So as I said, without a lot of detail, the theorem states that if we want to find the definite integral from a to b of f at x with respect to x, that we can actually use antiderivatives to do that. So we can find area under the curve, think back a few pages, by using that idea of an antiderivative that we just developed. And what we'll actually have to do is find the antiderivative, and evaluate it at b, then subtract the antiderivative evaluated at a. If you want more theory, the link there is a playlist that actually goes through the fundamental theorem of calculus in quite a lot of detail. Okay, the fundamental theorem of calculus I think will make a lot more sense if we can see a couple of examples. So in part A, you're asked for the integral from 1 to 3 of the function 2x with respect to x. And I don't want you to forget that that always means area under the curve between 1 and 3 of that function 2x. But now we have the fundamental theorem of calculus that says we can figure that out without drawing a picture and calculating areas. We can actually start with an antiderivative. So using the rule that we developed for powers, I think we can see fairly quickly that the antiderivative in that case is x squared, because we know that when we take the derivative of x squared, we get 2x. What you're seeing now is some new notation. What I'm going to do is put that in brackets with a 1 at the bottom and a 3 at the top. And what that signifies is that we're going to evaluate that at 3 and then subtract what we get when we evaluate at 1. So we're taking the antiderivative and subbing in a 3, we're taking the antiderivative and subbing in a 1, and we're subtracting the two results. The other way that you might see that written is just with this straight line after the x squared and the 1 and the 3 in the same fashion there. In any case, when we sub in a 3 squared and a 1 squared, we get 9 minus 1, which is 8 units. Let's try another one. Part B is pretty similar. It also uses the power rule. If we think of the antiderivative of x squared, again, we're increasing the power by 1, so that would be x to the 3, and we need a 1/3 in front to cancel out that 3 if we were to take the derivative. And the antiderivative of -3 is -3x. Again, because when you take that derivative of 3x, we get 3. Notice that we haven't added a constant. That's not necessary when we're working with definite integrals because in fact when we subtract, the two constants would cancel out. Our bounds of integration go here, that's a 1 and a 2, and it signifies that we're going to sub in a 2 and sub in a 1 and subtract the results. So always starting with the top number, let's sub in 2 cubed is 8, so we get 8 thirds minus 6 because 3 times 2 is 6. And then we're going to sub in a 1. So 1 cubed is 1. We get 1 third minus 3 times 1 is 3. And at this point, you could grab a calculator. You could find some common denominators. I'm going to be a little bit lazy and skip straight to the answer here. You'll find that we get negative 2 thirds. One more example. This time we want the integral from negative 1 to 1 of x cubed, and we know that we can do that by finding an antiderivative. The antiderivative in this case is 1 over 4 times x to the 4. It's the same rule we used in the 2 above, and we're going to evaluate that at 1 and at negative 1. We get 1 quarter times 1 to the 4 minus 1 quarter times negative 1 to the 4, which is just 1. So we've got 1 quarter minus 1 quarter, which is 0. We're going to take a look at the graph that goes along with part C, and my goal is to show you why an answer of 0 makes sense there. And I've said it a number of times, it's something I don't want you to forget. Integration tells us the area under the curve. And in this case, we were integrating from negative 1 to 1. So we started at negative 1 and integrated to 1. And remember, area under the curve is actually meaning between the curve and the x-axis. So we're talking about this area here and this area here. And I think that we can see that they're the same. The area below the x-axis is the same as the area above the x-axis. And we say that one is a positive integral and one is a negative integral. So if we've got an area of 1 quarter in both of those shaded regions, but one is negative 1 quarter and the other is 1 quarter, then it makes perfect sense that our answer is 0. So if you take away anything, remember that the integration tells us the area under a curve. And in this case, we get the net accumulation. We've accumulated 0 because what's under the x-axis matches what's above the x-axis. And I think that should give you the basics of what you'll need to know about integration for next year.